This is a state-of-the-art electric Formula E racing car. Its maximum speed can exceed 300 kilometers per hour, and it can accelerate from 0 to 100 kilometers per hour in less than 3 seconds. Similar to a rocket ship with wheels, it can dash along the track with remarkable speed and excellent performance. And this right here is the power core of electric racing cars, the permanent magnet synchronous motor. It comes with multiple advantages, including high efficiency, high power density, high response speed, and being lightweight. Under optimal working conditions, the efficiency of the permanent magnet synchronous motor can exceed 95%, which is far better than that of traditional internal combustion engines. The permanent magnet motors equipped in some of the top-tier electric racing cars can reach a maximum rotational speed of nearly 20,000 RPM and have a speed-adjusting capability of 150 RPM per millisecond. This formidable performance provides stable and powerful power support for the vehicles during startup, when climbing slopes, and in conditions of frequent acceleration and deceleration, fulfilling the demands of vehicles driving on complex and variable roads. Of course, such high performance will inevitably come with certain costs. When the motor is running at high speeds, it will generate huge eddy current losses. Eddy current loss is a phenomenon within electromagnetism. When a conductive material is placed in a changing magnetic field, an induced current is generated inside it. This current often forms closed loops that are shaped like whirlpools, which is why it's called eddy current. As the eddy current flows through the material, it encounters resistance and gives off heat. This energy loss is what we refer to as eddy current loss. Typically, when we talk about the energy losses in permanent magnet motors, we mainly focus on the iron losses in the stator and rotor as well as the copper losses in the coils. However, magnets, being non-insulating materials, can also generate eddy current losses in high-frequency changing magnetic fields. Take the sintered neodymium magnets used in high-speed motors, for example. Their resistivity is relatively low, and their temperature resistance is not very good either. If we add the situation of not-so-good heat dissipation in the rotor area, when the motor runs at high speed, the neodymium magnets are very likely to experience severe heating. Once the temperature of a neodymium magnet surpasses its working temperature, its magnetic property will decline. When subjected to high temperatures for an extended period, the neodymium magnet might even be completely demagnetized, and the permanent magnet motor will thus be scrapped. To prevent such an unfavorable situation from happening, we have to reduce the eddy currents within neodymium magnets. One of the most effective ways is to utilize laminated neodymium magnets. Before that, there's a concept we need to get acquainted with, the skin effect. It indicates that in a conductive material, when an alternating current flows through, the current has a tendency to concentrate near the surface of the conductor instead of distributing evenly across the entire cross-sectional area of the conductor. This phenomenon is especially prominent in high-frequency currents. This is an eddy current density diagram of a neodymium magnet operating in a high-speed motor. The eddy currents have formed a complete loop within the magnet. Evidently, because of the skin effect, these eddy currents concentrate on the surface of the magnet, resulting in a high temperature zone on the surface. So, what would be the difference if we made the magnet into a laminated structure? Laminated magnets consist of multiple magnetic sheets, and these sheets are glued together using insulating adhesive. Once the glue has fully cured, we can then machine it into whatever form we need. After the magnetization process is finished, a laminated magnet is successfully produced. As the magnet is cut into several small pieces and the connections are insulated by glue, the induced current can't form a complete eddy current loop within the laminated magnet. Instead, only tiny eddy currents are generated inside each small piece. This structure prevents the eddy currents from concentrating together and causing local high-temperature demagnetization. As can be seen in the graph, as the number of layers of the magnet segmentation increases, the eddy currents are distributed more uniformly across the magnet surface and bonding interfaces, and the maximum value of the eddy current density is also reduced further. Of course, this doesn't mean that the more times of segmentation, the better. Excessive segmentation may lead to a decline in the performance of the magnet. Each laminated magnet needs to determine how to design its structure finally according to its own volume and the working conditions of the motor. Besides laminated magnets, there is now a new alternative, the snakeline magnet. After experiments and calculations by cutting out appropriate serpentine grooves inside it, this magnet structure can also block the eddy current loops, achieving the effect of reducing the eddy current density. Moreover, it also avoids the complicated manufacturing process of laminated magnets. That's all for today. Thank you for watching. If you enjoyed it, don't forget to like and subscribe to our channel. If you're interested in our permanent magnet products, please contact us. See you next time.